Hello, I'm David Noel. Welcome to episode 10 of SMB. The topic today is the light from stars. Study of the light from stars goes back to very deep in our history. We've gained most of our knowledge of the universe from studying the stars. Back in episode 4, about black holes, we looked at the Hertzsprung-Russell diagram used to classify the stars in our local galaxy, the Milky Way. We saw in episode 4 that most of the stars we knew about in the early 1900s were those which fall on the main sequence of the HR diagram. These stars are called fusion stars. They produce energy by the fusion of atomic nuclei within them, and this energy is radiated out into their surroundings, mostly as visible light. These fusion stars are always assumed to radiate equally in all directions. We now know that this is not completely true, as the Sun has lighter and darker patches which radiate slightly differently, but it's close enough for our most purposes. Also back in episode 4, we saw that the stars called white dwarfs, towards the bottom of the HR diagram, are not fusion stars, but a totally different type of object called a vortex star. Vortex stars, which include white dwarfs, neutron stars and black holes, are a large class of rapidly rotating objects which emit tight beams of energy along their spin axes. The graphic is a representation of a vortex star. The image gives a feel for a rapidly rotating object emitting beams along its axes, but the reality is rather different. The beams which vortex stars emit are called tightly collimated. That means that they undergo very little spread along their paths. This is similar to laser beams, which also show very little spread. The fact that these beams are collimated leads to important consequences. First, because there is negligible spread, the beam can travel a very long way without losing much energy. A vortex star beam in open space will encounter occasional gas molecules, but these are sparse enough not to affect the main flow. Second, a vortex star beam will only be very obvious when viewed head-on, looking directly down the beam. When viewed at any other angle, the beam will be only apparent when it's hitting significant matter, which scatters the beam sideways. Photos of what are called galactic jets do show this behaviour. Thirdly, estimating the total energy emitted by a vortex star is difficult because it does not radiate in all directions, like a fusion star. This should be evident, but there's a surprising lack of acceptance at this point, even among professional astronomers. This leads them to hugely overestimate the energy given out by distant stellar objects. In all earlier days, when the importance of the orientation of the observer to the direction of vortex beams was not realized, vortex stars, which were actually fairly similar, were assigned to different classes. In this way, a vortex star might be called a radio galaxy, a Seyfert galaxy, a quasar, or a blazar, depending on the orientation of its beams. Fusion stars obey fairly strict rules regarding their masses, surface temperatures, and life histories. Vortex stars embrace virtually all the new types of celestial object discovered in recent years. As well as those just mentioned, the names include pulsar, neutron star, magnetar, AGN, supermassive black hole, and fast radio burst. Vortex stars also obey rules. All are rapidly rotating objects emitting radiation, and sometimes matter particles in axial beams. Higher mass vortex stars rotate more rapidly and radiate energy at higher frequencies. Our Sun, a typical fusion star, rotates once on its axis in about 25 days. A small vortex star, such as a white dwarf, may rotate once every 20 minutes. More massive vortex stars spin more rapidly. As of 2021, the fastest spinning one known was a so-called millisecond pulsar, which rotates 716 times a second. The vast majority of new celestial objects revealed by more powerful telescopes are the AGNs, or supermassive black holes, which exist at the heart of every galaxy. These are mostly ones which happen to have their axial beams pointing directly at us. The output of a fusion star is normally very stable, very fixed in quantity and nature. Vortex star outputs may also be very stable. However, conditions can exist, particularly with a vortex star in close proximity with a second star, where the radiation perceived on Earth is very variable, often cyclic. Before closing, we might look again at the HR diagram for the stars of our galaxy. We now know that the main sequence stars are normally fusion stars, while the white dwarfs are smaller vortex stars. The AGN, or supermassive black hole at the centre of our galaxy, is also a vortex star, but we cannot see its output because it's emitted at right angles to the plane of the galaxy. What about the giants and supergiants at the top of the chart? These are transition stars formed when a fusion star enters its blow-up phase. In the blow-up, the outer half of the star is blown away, eventually dissipating as a nebula, while the inner half speeds up and is eventually revealed as a vortex star. There's more on this in other episodes of SMB. Following is a link to a referenced article on the web, which gives more detail and links on the current topic. And finally, some links to other sources available to you. These include episodes on our YouTube channel and a website including articles which quote established and referenced data. May be worth following up. Thanks for watching. I hope these SMB episodes help in explaining how the universe works. Till next time then, goodbye from David Noel.